Okay, so today we'll discuss another important aspects of thermodynamics, that is, phase equilibrium in one component system. And what does that mean? We'll discuss. But prior to discussing that phase equilibrium in one component system, there are a few things I want to talk about. As you can see in this slide, there are this is very important equation, this Clausius-Clapeyron equation. Now, what is this all about? Now, let me give an introduction. What is this all about? See, this Clausius-Clapeyron equation is about equilibrium. Thermodynamics is always about equilibrium. So, whenever we talk about equilibrium between different phases, suppose ice is in equilibrium with water, what does this mean? This means that there is no change or conversion of water into ice or ice into water. I mean, the amount of moles of water remains constant, amount of moles of ice remains constant with time for the given condition. Okay, so what we mean by given condition? Normally, any thermodynamical condition is portrayed by its temperature and pressure. Remember, temperature and pressure. So temperature and pressure determine what is the exact amount of a phase. For example, what is the number of moles of liquid will be in equilibrium with the exact amount of moles of the solid of the same material. For example, we talk about ice and water. We normally say that, let's say, X gram of water is in equilibrium with Y gram of ice for a given temperature and pressure. So remember, temperature and pressure is very important. So temperature and pressure, for example, we say that at 1 atmospheric pressure, at 0 degree centigrade, certain amount of water is always in equilibrium with ice. So if you just add more water to the system, what will happen? Some amount of water will be retained, it will convert into ice. So apart from the composition, so actually you have three variables: composition, pressure, and temperature. So a fixed amount of composition, if you fix the composition, that is, you fix the amount of moles for solid and liquid, so you have a condition or a combination of pressure and temperature. So just for example, I will just come back to this equation once more once we are done with this. So this is the Clausius-Clapeyron equation, and sometimes referred as P2 ln P2 by P on is minus delta H vapor. We'll talk about this. And this is normally how the vapor pressure, this is between a condensed phase and a vapor phase. So how the vapor pressure varies with temperature. Remember, at each, this lines determines what? This determines for this given temperature and vapor pressure, this is the equilibrium conditions for a given amount of moles of liquid or given amount of moles of a phase is in equilibrium with the other phase. So for along this line there is no change in the equilibrium. What do I mean by that? Delta G is 0. So this is different for different material. For ethyl alcohol, this is for water. Look at this. This is a 100 degree centigrade, okay, and the vapor pressure is 1 atmospheric. We call this as a at 1 atmospheric pressure, the temperature at which liquid is in equilibrium, this water in equilibrium with ice, we call it as a standard vapor pressure or standard temperature of boiling. Sorry, this is equilibrium between water and steam. So at 100 degree centigrade, at 1 atmospheric pressure or 760 atmospheric pressure, water is in equilibrium with its vapor. But always remember, there is also mole involved. You cannot just add more amount of moles or you cannot just add more amount of water. So there is the equilibrium condition determined by the vapor pressure and the temperature. So this is between a condensed phase and a vapor phase. Condensed phase here is the water and vapor phase is the steam for water. So at 100 degree centigrade, the 760 torr, it's in the unit is torr. Water is in equilibrium with vapor pressure. That means at these conditions the delta G is 0. Okay, fine.